Chapter 3, Exercise 5, Part A. Assume that A and B are given sets and show that there exists a set C such that for any y is in C if and only if y is equal to the cross product of the set containing x and B for some x in A. In other words, show that the set containing every set of the form the set containing x cross product with B such that x is in A is a set. That is the most weird way I've worded a set ever. I'm sorry if that wasn't clear, but yeah. I write the, in case you are visually impaired, I write the problem statements in the description, so hopefully your screen reader will do a much better job of explaining this than I did. But I hope this becomes more helpful as the video goes along. Anywho, part B, with A, B, and C is above, show that A cross B is equal to the union of C. Right, so this question is, it was hard. I think it was pretty hard for me because it involves a proof strategy that I hadn't seen before. And it kind of follows in the same vein as the last question of asking, which sets are constructible, which sets are not constructible. There's a whole discussion on page... What am I going to... where is it? Pages 37 and 38. I'll just make an annotation here. Circle it, why not? Okay, so especially when defining the set, or rather the cross product of any two sets, right? Like when is it legal? Is it always legal? Or, is it the case that when you construct a cross product of two sets, then you end up accidentally creating a set of all sets, or do you end up creating some other set that is illegal? Like we showed in exercise 4, if you construct a set of all ordered pairs, then you also implicitly construct the set of all sets, which is a big no-no. So I think Enderton takes this somewhat philosophical discussion and just tries to put this in this exercise, because technically you can define a set loosely. I'm using the word define very loosely to be whatever you want, right? But it is kind of your responsibility to show that it is indeed a set and that it is legal. So here we're constructing this set specifically, right? Or rather, we're constructing this set. But we want to show that it is indeed a set and that we're not just making up gibberish because we just string together words that sound mathy or set theoretic. Right, and the approach that Enderton uses is to use the subset axiom, and in particular what he does is he finds a larger set of which his desired set is a subset in particular, and I'm just gonna move this down. Oh, what the hell? Alright. Okay. In particular, he shows that A cross B is a subset of, I think it is the powers of the power set of A union B. Let me not lie to you and actually look this up. Page 37. It's so nice to have the physical book, by the way. Right. Yeah. Yeah, this is right. So he shows that this is true, and then by the way we've set up our axioms, if you take the subset of any set you want, then that subset is a set, and you're kind of in the green for that. So that is the approach that we're going to take in this video. We're going to try to find some larger set of which this is a subset, and then we're just going to invoke the subset axiom and then call it a day. Okay, so, right, so how do we go about doing this? We want to find a set such that y is in our set, the cross product of the set containing x and b, such that x is in A, implies that y is in this other superset S. Okay, so I'll just write down a couple facts. And why not write them in pink? Because that is more colorful. It looks better. So, our first fact, oh my god, is that A cross B is a set for any sets A and B. And the second fact is that the power set of A is a set for any set A. Right? Okay. So, in particular, let's see how exactly we're going to construct this superset. So, if y is in this set, then y is equal to the cross product of the set containing x and b for some x in A. This means that that for any A comma B, or rather let's call them x comma B, in this set. Right, yes. Sorry. It's just this is a bit confusing to word. I can do a recap at the end if it's too confusing. So anywho, for any pair that we find in this cross product, x is going to be in the set containing x, and b is going to be in this larger B. Okay, right? We know that x is in A, which implies that the set containing x is in A, and this might seem a bit redundant, but I'm just like making sure that what I'm saying is not just dependent on symbols, right? Because this symbol x is a bit overloaded at the moment. I'm gonna actually redo this with a different symbol. The thing is, it's a little confusing if you do it with or without the same symbols, right? Anywho, x is in A implies that the set containing x is actually not in A, but a subset of A, which implies that if x is in A, then x is in A. Okay, so what I was going to do originally is say that if A comma B is in the set containing x cross B, then A is in the set containing x and B is in the set big B. So if, and this is the exact same argument, if x is in A, then the set containing x is a subset of A, which implies that, so if A is in the set containing x, then A is in A. That actually was a lot less confusing than I saw it in my brain. Okay, all this to say that AB satisfies that A is in little a is in big A and little b is in big B. So A comma B is in the cross product of big A and big B. Right? Now this means that y, which is equal to the set x cross b, is a subset of A cross B, which implies that y is in the power set of A cross B. Again, taking the cross product of any two sets is legal. The power set of any set is legal. Right? Okay. So, and this to say that this set specifically is a legal set. So, y being in the set of containing x cross b such that x is in A implies that y is in the power set of A cross B. This means that this set S, or rather, this means that this set containing x cross B such that x is in A is a subset of the power set of A cross B. So our set is indeed a set by our subset axioms. Right. So we worded it as S. So to reiterate, S is going to be the power set of A cross B. Yep. Cool. So there you go. That is how you show that this set specifically is indeed a valid. And now for part B, we want to show that with these sets being as we've just shown them, power set of A cross B is equal to the union of C. And C oh right, we could have just called this set C the whole time. Okay, I did not notice that, but I'm too far deep in this video. So recall that C, or rather A and B are sets, big A and big B that is, and C is equal to the set of cross products of set containing x cross B such that x is in A. Okay, now suppose and we're going to do a regular set equality proof, show that this is a subset of this subset of that. Suppose now that A comma B is in the cross product of big A and big B, then A is in A and B is in B. A is also in the set containing A. So our ordered pair A comma B satisfies that A is in the set containing A and B is in B. So there exists an x in A, namely little a, such that A comma B is in the cross product of the set containing x and b. And this means that A comma B is in the union of C, as we have done several times in this channel. Okay, so A cross B is a subset of the union of C. Right. Now suppose A cross B is in the union of C instead. Then there exists some x in A such that A is in the set containing x and B is in big B. Okay, so what this means is that since x is in A, and the set containing x is a subset of big A, so A is in, little a is in big A. Thus, our ordered pair A comma B satisfies that little a is in big A and little b is in big B. Right? So A comma B is going to be in the cross product of A and B. Thus, the union of C is a subset of A cross B. And we conclude that the two sets must be equal. And there you have it. That is all of exercise 5. Yeah, I hope this was helpful. If this was way too confusing and I should, you can ask clarifications in the comments. And if you think I should reshoot the entire thing, then leave a dislike. Otherwise, likes are welcome, not necessary. Comments, especially if you're showing me something I did wrong, or if you can clarify something that wasn't completely clear, are very welcome and very appreciated. With that said, I will see you in the next video. Bye-bye.